Welcome everyone to our EIGRP Deep Dive. And for those of you that don't know me, my name is Kevin Wallace, and I'm thrilled that you joined me here at the beginning of 2022. Those of you watching on replay, I normally do these sessions on New Year's Day. This year's a little bit different. On New Year's Day, my daughter and her husband, they were moving into their brand new house. So I was lugging furniture and hooking up stuff on New Year's Day. So we pushed it out a few days, but I still wanted to spend some time with you and do a deep dive training here at the beginning of the year, the beginning of 2022. So thank you for joining me. I really appreciate it. And we're going to be diving deep into the Enhanced Interior Gateway Routing Protocol, or EIGRP, today. And that's one of the protocols that you need to know specifically for the ENARSI exam. If you're going to be going after your CCNP and Enterprise, that's the most popular concentration exam. You've got to take Encore, the core Enterprise course in that exam. But then you can pick a concentration exam. And from what I've seen, most people are going with ENARSI. And this is where EIGRP really shows up. It shows up a little bit in Encore, but it shows up in a big way in ENARSI. So we want to cover today everything you need to know to master the EIGRP topic on your ENARSI exam. And as far as the runtime, I'm guessing it's going to be between 2 and 3 hours today, just a guess. And here's specifically what we're going to be covering. We're going to begin by just discussing the fundamentals. What makes EIGRP different than something like OSPF? We'll talk about the timers. Those are very different from OSPF as well. We'll talk about how metrics are calculated. And if you've never seen the EIGRP metric calculation formula, brace yourself. It is a doozy, but we'll simplify it for you. We'll see how EIGRP makes its path selection decisions. And one way it does that is to have another route or maybe multiple routes, if it can, on standby. So if a primary route fails, it has what are called feasible successor routes. So if the successor route goes down, then it's going to be able to say, all right, I've got another backup route that I can cut over to almost immediately. If that's not available, there's another one I can cut over to almost immediately. In order to qualify, though, as a feasible successor, we've got to meet a condition called the feasibility condition. We'll dive into that today as well. We'll talk about what EIGRP does if it loses a route and there is no feasible successor. It's going to send out a query throughout the network saying, hey, does anybody know how to get to this network I just lost connectivity to? And we'll talk about an issue that, well, it used to be an issue. It's called stuck in active. We'll see what used to result in a stuck in active condition. Got lots of demos coming up today. The first one will be on just a traditional EIGRP configuration for IP version 4 networks. We'll talk about stub routing. That's different than stub areas in OSPF. We'll talk about what stub routing means in EIGRP. We'll demonstrate that. We'll demonstrate how to configure a passive interface. We'll talk about something that makes EIGRP unique from other routing protocols, its ability to load balance across unequal cost paths. Yeah, RIP, OSPF, they can load balance across a couple of paths or more if they have an equal cost, but EIGRP can proportionately load balance traffic across unequal cost paths. And it's called the variance feature. We'll see how to set that up. And we'll talk about how we do route summarization. Again, if you joined me for my OSPF deep dive a few weeks ago, summarization in EIGRP, it's quite different than it was in OSPF. We don't have as many restrictions. I'll demonstrate that for you. Then we'll talk about how EIGRP for IP version 6 is going to be configured. We'll do a traditional configuration. That's where we set up EIGRP for IP version 4, and then separately, or in addition to that, we set up EIGRP for IP version 6. But then we take a look at a new, better way of doing it. It's called named EIGRP, where we create one hierarchical structure, and underneath that structure, we configure everything. We configure all of the IPv4, all the IPv6, all of the different parameters. It's all under one structure. It's called named EIGRP. You're going to love that. And finally, we're going to talk about how to do authentication. We don't want somebody just to introduce a rogue router into the network and start advertising false EIGRP routes. No, we want to have our EIGRP routers authenticate with one another so they're going to be trusted. Now, for those of you that don't know me, here's my super quick bio, and then we'll jump into the content. But again, my name is Kevin Wallace. I've been doing this for quite a while. I've got a couple of CCIEs. I've got a CCIE in enterprise infrastructure and another one in collaboration. Been working with this stuff for well over 3 decades now. I worked with the very first model of Cisco router, the old Cisco AGS Plus, back around 1989. And I was a instructor for Cisco Learning Partners for about 14 years. And then back in 2014, I decided to go out on my own. So I've been doing this full time. I've got my own training company now, and we create courses and do live trainings and do lots of webcasts like this to try to really simplify IT concepts for everyone. Real world experience includes several things, but one of my favorite jobs, I've got to tell you, was when I was a network design specialist down at Walt Disney World in Florida. My family and I, we are huge Disney fans. I often integrate some Disney stories throughout my training. In fact, there's one coming up today when we talk about EIGRP's metric calculation. I've got a Disney story for you. But yeah, I was one of 5 network designers down there, and they were all EIGRP across the Disney World property. So I've worked with a very, probably the largest EIGRP network that's out there. I've written a bunch of books, done a lot of videos for the folks over at Cisco Press, and I spoke at a couple of Cisco Live conventions and was honored to get the Distinguished Speaker Award each of those times. Bottom line is, I love this stuff. I'm passionate about this content, and I cannot wait to spend the next 2 or 3 hours sharing it with you. So let's jump into our first module, module number 1, EIGRP Fundamentals. Now, when we think about EIGRP, what are some overlaying characteristics if we were to look at some of the major bullet points? Well, number 1, it's got super fast convergence in a lot of cases. If it has that feasible successor standing by, if the successor, the primary, the preferred route goes down, that feasible successor can take over in like a couple of seconds or so, about like OSPF, much faster than RIP. And it is scalable. RIP, we know, is not very scalable. We've got that 15 hop count maximum, and then 16 hops are unreachable. So it is very scalable. I mean, that's as evidenced by Disney World. We had over 500 routers down at Walt Disney World, and yeah, all running EIGRP. And the thing that really makes it unique compared to other routing protocols is that EIGRP has that very interesting ability to load balance across unequal cost paths. And we'll see how to set that up today. We can do classless advertisements. In other words, when I advertise a network, it doesn't have to have a classful mask. It's classless advertisements, I should say. It doesn't have to have a classful mask. In other words, I could advertise something with a /22 mask or /27 mask. It doesn't have to fall neatly at a classful boundary. And it's going to communicate with other EIGRP speaking routers using multicast. Not broadcast like RIP version 1 used to do, but multicast. And if it's an IP version 4 speaking neighbor, we're going to use the well-known multicast address of 224.0.0.10. If it's IPv6, it's going to be FF02::A. And this used to be a Cisco proprietary routing protocol. When I worked at Walt Disney World, this was when it was a Cisco proprietary protocol, and we were an all Cisco shop, so that was fine. Over 500 Cisco routers, literally thousands of Cisco Catalyst switches. But around 2010, Cisco said, all right, we're going to start opening this up to some other vendors. Now, originally, they didn't open everything up. They just allowed a few features to be opened up, and later they opened up some more. So it technically is available to other vendors, but this is just my observation. It kind of seems like other vendors said, no, we're good. Thanks anyway. And there was not a large scale adoption of EIGRP among other router vendors. Now, there was some. The implementations that I've seen among other vendors involve just enough EIGRP to allow you to transition from your EIGRP speaking Cisco network to your maybe an OSPF speaking network from a different vendor. So they would help you transition over to their platform using EIGRP, and then you could migrate to something like OSPF. But let's talk about architecturally the 4 components that make up EIGRP. Number 1, it is capable of doing neighbor discovery dynamically. We don't have to hard code in the IP address of our neighbors. And when it sends routing advertisements back and forth with those neighbors, it's going to do so with reliability. It's going to make sure those advertisements are acknowledged. Now, to keep the overhead down, not everything is acknowledged. Occasionally, we're going to see that we're going to be sending these hello messages to a neighbor, and we don't have to have an acknowledgement for a hello message. That would create a lot of extra overhead. So not everything gets acknowledged, but we're going to use the Reliable Transport Protocol, or RTP, to make sure that those routing advertisements really did get to our neighbor. And the way we make that pass selection decision is using an algorithm called DUAL, the diffusing update algorithm. You might remember OSPF, it used the Dijkstra algorithm. Well, EIGRP uses the diffusing update algorithm. And we'll talk about how that works a little bit later today as well. And something that also makes EIGRP kind of unique is that it's protocol independence. In other words, it is capable of routing more than just one protocol. And that's changed over the years a little bit. Right now, when I say it's going to route multiple protocols, it's going to route IP version 4 and IP version 6. But when I started working with EIGRP way back in, I guess, the early to mid, sometime in the 90s, I was working on a network that routed not just IP version 4 traffic. We routed Novell's IPX traffic. We routed Apple's Apple Talk traffic, if anybody remembers those. EIGRP could have a routing structure, a routing table for IP version 4, IPX, and Apple Talk. So it's allowing us to have one routing protocol route for multiple routed protocols. But again, today that's probably going to be EIGRP for IP version 4 and or EIGRP for IP version 6. And when we get into looking at some of the show commands, here are the three tables that EIGRP maintains. There's one table that says, here's your neighbor. Another table says, here is a list of interfaces participating in EIGRP. And another table is the topology table. That's the routing information known or learned by EIGRP. Oh, the one thing on the interface table, let me back up to that one for a second. When I say an interface is participating in EIGRP, what I mean by that is the network to which that interface's IP address belongs, that network is being advertised by EIGRP. If you join me for our OSPF deep dive, we talked about when we were configuring the network command, we said network, and we gave a network address, and we gave a wildcard mask and an area. Well, we said that network command and the wildcard mask, we said that was not saying advertise this network. We were saying here is an IP address space. And if you have an interface that has an IP address that falls within that address space, advertise that interface's network. So the wildcard mask that we apply, which is just like the reciprocal of a subnet mask, that's not necessarily what we're advertising. We're just setting an IP address space. And if an interface, let me say it again, if an interface has an IP address that falls within that address space, that interface's network, even though it might have a different subnet mask than the network statement as compared to its wildcard mask, we're going to advertise that interface's network. We'll see that coming up in just a bit. Now, that wraps up this high-level overview of EIGRP fundamentals. Next up, let's talk about timers. Because when we've got a couple of EIGRP routers and they're talking to one another, they need to make sure that neighbor is still up and available. They need to initially form a relationship with that neighbor. And that is done through hello messages that are sent out to those multicast addresses we were talking about earlier. We got a couple of timers. Now, by default, on an Ethernet network, we have a hello interval and a hold time timer. Now, the hello interval defaults to 5 seconds. So every 5 seconds, my neighbor is going to be sending me a hello message saying, hey, I'm still here. And if I've not heard from that neighbor, by default, we can change it. But by default, if I've not heard from that neighbor within 15 seconds, I'm going to say, whoa, I don't think they're there any longer. They should have sent me like 2 or 3 messages between in the last 15 seconds. So we're going to tear down that neighborship. So yeah, we could lose 1, maybe even lose 2 hello messages. But yeah, if we have 15 seconds elapse and no hellos, we're going to consider them down. So it looks kind of like this. We start out with a 15-second timer. We count down to about 10, and then bam, we go back up again. Now, when you're looking at this real time, I never see 15 seconds. It always goes down to 10, and then it jumps right back up to 14. So I guess we're just a hair under 15 seconds. We'll take a look at that in the live interface in just a few moments. But when we receive that next hello packet, the hold time timer, it resets to the full 15 seconds. Now, this is going to be different than the way OSPF worked. It sounds similar, but it's different. Let me explain. With OSPF, we've got a couple of timers called the hello interval and the dead interval. And the hello interval says how often or how frequently am I going to be sending out a hello message. And the dead interval says if I've not heard from my neighbor within this amount of time, I'm going to consider them to be down. That's the way OSPF works. And a lot of people assume that's the way that EIGRP works as well, with its hello interval and its hold time. Actually, it's not. Now, the hello interval is about the same. If I'm router R1, and let's say you're router R2, and I've got my default hello interval of 5 seconds, I'm sending you a hello message, a multicast, every 5 seconds. But my whole time I said defaults to 15 seconds. I am not saying necessarily, I'm not saying, all right, my whole time is 15 seconds. So if I don't hear from you within 15 seconds, I'm going to tear down this neighborship. That's the way OSPF does it, but the whole time works opposite in EIGRP. Let me explain. Instead of the whole time being how long I'm going to wait on you, the whole time is how long I tell you to wait on me. It's like in the movies where you're going into the deep, dark cave and you say, if you don't hear from me within 20 minutes, send help. That's kind of what we're doing here. I'm saying, if you don't hear from me within 15 seconds, consider me to be down. So I'm not saying I'm going to wait on you this long. I'm saying I want you to wait on me this long. And by default, we're each going to have a 15-second hold time, but they don't have to match. It's a good practice to make a match, but we could have different timers. Because let's say that I set my hello interval to 10 seconds and my hold time to 30 seconds. Okay. That means I'm going to be telling you to wait on my hello messages, which are coming less frequently. Wait on me for 30 seconds. If you don't hear a hello message from me within 30 seconds, you can consider me to be down. So that's the distinction between EIGRP and OSPF timers. Next up, we want to talk about how EIGRP calculates its metric. And it's sort of complex, to be honest. We know with RIP, pretty easy. Hop count. How many routers do I have to hop through to get to a destination network? With OSPF, it's based on bandwidth. It's the reference bandwidth divided by the interface speed. That's our cost. With the EIGRP, it's a little bit more involved. In fact, there's an acrostic that I memorized a long time ago that let me remember the elements that could go into an EIGRP metric calculation. And here's the acrostic if you want to write it down. It's big dogs really like me. Big dogs really like me. Where the B in big reminds me of the B in bandwidth, and the D in dogs reminds me of the D in delay, and the R in really reminds me of the R in reliability, and the L in like reminds me of the L in load, and the M in me reminds me of the M in MTU, the maximum transmission unit. So to give you one of those Disney stories I was telling you about, when I was doing my technical interview for them, they asked me, because they ran EIGRP everywhere, I was up at the whiteboard and they said, all right, tell us, by default, what does EIGRP use to calculate its metric? And I thought, I got this. I know this acrostic. Big dogs really like me, so I just rattled it off. I said, bandwidth, delay, reliability, load, MTU, and they said, no, you're wrong. What do you mean I'm wrong? Big dogs really like me. They said, no, we said, by default, what does it consider? Oh, by default, it's only going to consider bandwidth and delay. And most of the time we leave it at just that. But if we want to consider reliability, if we want to consider the load that's on a circuit, we can factor those in. Now, interestingly, MTU, the maximum transmission unit, that was designed as a tiebreaker. It doesn't even factor in to this formula. Now, are you sitting down? Brace yourself. Here comes the formula. It's a doozy, I said. Yikes. There is the metric formula for EIGRP. And you're going to see that we've got some constants, some K values. And these K values can take on various integer values, so we can give more weight or less weight to like load or reliability or delay. Now, when we say bandwidth is the weakest link. If I've got a gig link connecting these two routers, and I've got a 100 meg link connecting these two routers, I've got a 10 gig link connecting these two routers, the bandwidth is going to just focus on that weakest link, the slowest link, the 100 meg link. And it's going to be 10 to the power of 7, 1 followed by 7 zeros, divided by that 100 meg, that 100 million. That's going to be my bandwidth. Now, delay is measured in an interesting way as well. Delay is measured in tens of microseconds. Tens of microseconds. So if you were to look at, in fact, let's just go out really quick and look at one. Here we are on a router. I'm going to say show IP or just show interface gigabit 0/1. This interface has a delay of 10 microseconds. Well, when we're using that EIGRP formula, the unit of measure is in tens of microseconds, so that would be a delay of 1 as we exited that interface. Reliability is a fraction. It's a number over 255. If we're not dropping anything and we're 100% reliable, then it's 255 over 255, which is 100%. Load is also a fraction over 255. A minimal load, if we're not using much or any of our bandwidth on this link, it's going to be a 1 over 255. And if we're totally saturated, it's going to be 255 over 255. Now these K values, we've got K 1, 2, 3, 4, 5. Here are the default K values that we have. And if you plug and chug, you'll see that with all these zeros, a lot of this equation just kind of disappears. In fact, if you're really attuned here, you might notice that, hold on, Kevin, K5 defaults to 0. K5 divided by K4 plus reliability, that's going to be a 0, and we're multiplying everything's going to be a 0 by default. There's an exception to this formula. This is the official formula, but there's a caveat. The caveat is if K5 equals 0, then that little element right there that says K5 divided by K4 plus reliability, that suddenly equals 1. I know mathematically it should equal 0, but that's an exception. If K5 equals 0, then K5 divided by K4 plus reliability, that equals 1. Notice that MTU does not play in here anywhere. That is just meant to be a tiebreaker. And here's an example. Let's say that we're sitting on router R3, and I'm wanting to see what the cost or the metric would be to get up to that network between R1 and SW1 at the top of the screen, the 192.168.1.0. What I would do is I would find the bandwidth of the weakest link. Now, right now, everything is a gig link. So we take 10 to the power of 7, so a 1 followed by 7 zeros, and we divide by a gig. Now, I should have pointed out that the unit of measure here is in kilobits per second. So 1 gigabit per second is 1 million K. So it's 10 million divided by 1 million K. And that's going to give us a value of 10. Every time we exit a gig interface, we're adding on 10 microseconds of delay. And this is not the weakest link, it's cumulative. So I add 10 microseconds of delay as I exit R3. I add another 10 milliseconds of delay as I exit R2. Actually, this is probably this is going to be the metric for not that top network, excuse me. It's going to be the metric for that network between R1 and R2, the 192.0.2.0, because I'm exiting, in this formula I just noticed, I'm exiting two interfaces. So I'm exiting that top interface on R3, I'm exiting that top interface on R2. That gets me to that network. So it's 10 microseconds each time I exit an interface for a total of 20 microseconds. But the unit of measure is tens of microseconds, so it's 20 divided by 10. So if we plug and chug here, it's 10 plus 2, 12, multiplied by 256. So that's going to give me a metric of 3,072. That's how the metric calculation works. Not incredibly straightforward, but that is the way it works. Let's take a look at how EIGRP does its path selection now. It's going, well, let's take a step back. When we talked about OSPF, we said that it was a link state routing protocol. In other words, it had a map of the overall network. And with this map of the network, it could see all the interconnections. It could run the Dijkstra algorithm and say, well, what if I went from here to here or here to here? It can consider all possibilities and it would go with the lowest cost. We don't have the luxury of having a map of the network with EIGRP. It's a distance vector routing protocol. Some people will argue it's a hybrid. I'll argue that, no, it's not hybrid. Hybrid implies we have both link state and distance vector components. We don't. We just have distance. It's advanced distance vector, I'll give you that, but it's certainly not hybrid, and it's certainly not link state. It's an advanced distance vector routing protocol. And since we don't have the luxury of having a map of the network, here's the way it works. Here's the way that dual algorithm works. Let's start talking about it. Let's say I'm on R3 and I'm trying to get to that network on the left-hand side of the screen, 10.1.1.0/24. Well, I could get there via one of two ways. I could get there via R1 or I could get there via R2. Now, R1 is going to have a cost or a metric of 1,000 to go out of its interface to this link. And R2 is going to also have a cost of 1,000. But R1, it says, all right, it's going to cost me 1,000 to get to this network. So it reports that to me. It's called the reported distance, or the RD. Now, some literature will call it the advertised distance. I don't like to use that term because AD, that makes it sound like administrative distance. But you might see either one, but I prefer to say reported distance. R1 is reporting to R3, hey, it's going to cost me 1,000 to get there. But R3 realizes it's going to cost something just to get to R1. What is that cost? Well, that cost, we'll say, is 10,000. So if I add up the 10,000 that it cost me to get to R1, I add that to what R1 reported, the reported distance, that's going to be a grand total of 11,000. That's called my feasible distance. So again, two different distances we're talking about here. What my neighbor is saying their cost is, that's the reported distance. The cost to get to my neighbor plus the reported distance, that's my feasible distance. R2, like I said, also has a cost of 1,000 to get to that network. And to get to R2, it's going to cost me 5,000. Okay, what is the feasible distance then? It's the cost to get to R2 of 5,000 plus R2's reported distance of 1,000. 5,000 plus 1,000, that's going to give me a feasible distance of 6,000. Well, I'm going to go with the lowest cost. I'm going to go with the R2 path because it has the lowest feasible distance. That becomes my successor route at that point. And R1 is a backup path that I can fail over to almost immediately. That's going to be my backup. That's going to be my backup, called my feasible successor. However, just because there's an alternate path to get to this network, that does not automatically make it a feasible successor. There's a rule, and I'm going to spend some time on this one because this confuses a lot of students. First of all, let me just read the rule, and then we're going to break it down. But here's the feasibility condition. This is the requirement for a route to become a backup route that we can fail over to almost immediately. It reads like this. An EIGRP route is a feasible successor route In other words, a route that we can fail over to in just like a couple of seconds. If that route's reported distance is less than the feasible distance of our successor route. Now, that might have sounded confusing when I read that, but we're going to break it down. What I'm saying is, if R5 is going to be a feasible, if going to R5 is going to be an alternate way to get to a network, and I want it to cut over to it almost immediately, I want it to be a feasible successor, then its reported distance to me, it needs to be less than the feasible distance. In other words, the total distance going over my preferred path. Why would we have such a seemingly arbitrary rule? Let me show you. We want to prevent a situation like this. You see, R1 does not have a map of the topology, unlike OSPF would have a map of the topology. And R1 is receiving advertisements from R2, R3, and R4 saying, hey, each of us are saying we'll get you to 10.1.1.0/24 because they all know how to get there, and they're advertising that to R1. Well, notice that R4 is dependent on R3 to get there. So let's say that R2 was the successor route. That was the preferred route. Bad news, let's say R2 goes down. Okay, we got a feasible successor in R3, so R1 starts going to this network via R3. What if it goes down? Well, R1 might say, well, R4 said it could get me there. Let's just go to R4. But you see, that's not going to work. It's not going to work because R4's way to that network was via R3, which is already down. So in an attempt to prevent something like this, the feasibility condition says, yeah, if your reported distance is not less than the feasible distance of my successor route, yeah, I've got some doubt that you're really going to be able to get me there. So you're not going to be cut over to almost immediately. That's not to say we would never use a backup path that was not a feasible successor. I'll show you when we would, but that is the feasibility condition. So let's go through another example. Here, would you agree with me that R2, R3, R4, they're equally capable? Well, not equally, they've got different costs, different metrics, but they are each able to independently get me over to 10.1.1.0/24 on the right-hand side of the screen. So if R2 went down, I could cut over to either one of those and it would give me a path. None of those routers, R2, R3, R4, they're not dependent on one another, is what I'm getting at. So let's take a look at all the distances involved here and how R1 is going to pick the best path over to 10.1.1.0/24. First, router R2 is advertising a reported distance of 6,000. Do you see where that comes from, by the way? R5 can get to this network with a cost of 1,000. It's a cost of 5,000 to get from R2 to R5. So total, from R2's perspective, it's 6,000 to get to this network. So R2 is going to report that number of 6,000 to me, to R1. It's going to cost me 10,000 to get to R2, so the total distance, in other words, that 10,000 to get to R2 plus R2's reported distance, 10,000 plus 6,000, it's going to be 16,000. What about R3? Well, R3 has a reported distance of 10,000 plus 1,000. It's got a reported distance of 11,000. It's going to cost me 7,000 to get to R3, so 7 plus 11, that's going to be a feasible distance of 18,000. And finally, R4, oh wow, it's a slow link there, it looks like, or a saturated link possibly. We're going to be able to get to 10.1.1.0 from R4 by going over to R5 with a metric of 17,000, and then out of R5 with a metric of 1,000. That's 18,000. R4 is reporting a distance of 18,000, and it's going to cost me 4,000 to get to that. That's a whopping feasible distance of 22,000. Now that we have the feasible distances of all of our neighbors, let's ask, which, if any of these, are my successor or feasible successor routes? Again, the successor route, that's the preferred route that I want to use. And the lowest feasible distance is going to be my successor or my preferred route. And the lowest feasible distance is via R2, so easy. R2 is my backup, or R2 is my primary path. But do I have a backup that I can fail over to almost immediately? Well, let's see. If I take a look at R3 and I look at its reported distance of 11,000, I have to ask, does that meet the feasibility condition? Remember what that is? R3's reported distance has to be less than the feasible distance of my successor route. So we ask the question, is 11,000 R3's reported distance? Is 11,000 less than 16,000? Which is the feasible distance of my successor path? Yeah, 11,000 is less than 16,000. So I know that R3 is not dependent on R2 to get to this network. And it's going to therefore become a feasible successor that I can fail over to almost immediately. What about R4? Now, we can see visually that R4 is not dependent on either R2 or R3, but it's going to fail the feasibility condition because its reported distance of 18,000, yeah, that's not less than the feasible, that's not less than the distance of our successor route, the feasible distance of our successor route of 16,000. 18,000 is not less than 16,000, therefore, we cannot use that as a feasible successor route. Now, that's not to say we could not use it at all, because we could. What we could do is, in the event we run out of feasible successor routes or paths to get to a destination network, we can send a query out through the network saying, hey, does anybody know how to get us to this particular network address? We send out these query messages. For example, let's say that R1 is connected out of its top interface. It's connected to 192.168.1.0/24. Bad news, that link just went down. Now, R1 does not have a feasible successor to get it there. Now, R1, because it does not have a map of the topology, now you and I can look at that and say, R1's out of luck. There is no backup path to that network. R1 doesn't know that, though. It just knows it doesn't have a feasible successor, so it goes in search of one. It goes into a different state. It's called the active state. And in that active state, it is going to be querying to see if anybody else knows that if anybody else knows a way to get to 192.168.1.0. So it sends out a query to R2, which is going to flood it out all of its other interfaces down to R3 and R4. They're going to flood it out of all their other interfaces, R5, R6, R7, R8. And then the responses come back. In this case, everybody's going to reply and say, sorry, no, we don't have a way to get there. And then R1 will then take that route out of its routing table. However, there used to be an issue with EIGRP. This was one of the big troubleshooting issues that we used to have back around the time I worked at Disney, back around the year 2000 or so. We got into a situation where we could become stuck and active. It was called the SIA condition, stuck and active. Because when we're querying and we're trying to get a response back to say, hey, is there another way to get to this network? We're in the active state. Here's a way that we might get stuck in that active state. Let's say that same thing happens. That network goes down. R1 says, oh, shucks. Let's see if there's another way to get there. So it starts to flood out these queries throughout the network. And just as before, it goes down to R2 and then down to R3 and R4 and R5, R6, R7, R8. And as the responses start to come back or the replies start to come back, things get dropped in the network from time to time. Let's say that the response from R4 gets dropped. That reply does not make it back to R2. Well, R2 has got a timer set. It says, I'm going to wait for 3 minutes to get a response, at which point I'm going to say, I don't think that lives down there. I didn't get a response from my neighbor. So I'm going to prune off that entire link going down to R4, R7, R8. So we set a 3-minute timer, both on R1 and on R2, because R1 was the one that initially sent the query. So after 3 minutes, if we don't hear a response come back, R2 is going to say, well, I'm going to prune off R4 and everything below it because it's not talking to me anymore. We dropped a packet. It happens. But it's going to prune everybody off if we don't hear from it within 3 minutes. It gets worse than that. R2, waiting for that response, never responds to R1. And as a result, R1 said, R2 didn't respond to me, so I think R2 is no longer available. So that will cause R1 to prune off the rest of the network. It prunes off R2, R3, R4, R5, R6, R7, R8. It's all gone. because it didn't hear back from R2. That's stuck inactive. That's the SAA condition. In later versions of Cisco iOS, it got a lot better. Here's the way it works today. But I wanted to explain it because you might hear of the SIA condition. Here, if the same thing happens, the queries flood down, the responses come back, but we drop one of the responses. Remember I said we had this 3-minute timer, and if we don't hear from our neighbor within 3 minutes, we chop it off? Well, at half that amount of time, after 90 seconds, here's what we're going to do. After 90 seconds, we're going to say, I haven't heard from my query yet. I'm a little concerned. I'm going to go proactively ask my neighbor, hey, did you not respond to me because maybe a packet got dropped? Did you not respond to me because you're waiting on a response from one of your downstream routers? Or did you not respond to me because you're down? So we're going to send another query after just 90 seconds. We're not waiting for the 3 minutes. We're going to send what is called an SIA query, a stuck inactive query, to say, hey, are you still there? You know, I asked you a question. I haven't heard anything back. And in this case, R4 is going to respond to R2 with an SIA reply saying, oh, I'm so sorry. Yeah, I sent it. I guess it got dropped. Here it is again. When R2 gets that, it then responds with a stuck inactive reply up to R1. And now everything's happy. Well, it's not totally happy because nobody found an alternate route to get to 192.168.1.0. But the bottom line is, with EIGRP, we've got our successor route. That's the preferred route. If other routes can get us to that same network with a higher metric, we'll make those feasible successor routes that we can cut over to in just like 2 or 3 seconds if, and only if, they meet the feasibility condition. Even if we don't have a feasible successor that meets the feasibility condition, that does not mean that there's not some other path out there that would get us to this network. We just have to query for it. So that's what the query process does for us. So that's a look at a lot of the theory of EIGRP. Let's get into a basic configuration right now. So let me hop over to our topology. In fact, I'm going to bring up this topology for you on screen, and I'll take my face off the screen so you can see it a bit better. There we go. There's a topology over on the left-hand side, and here we're sitting on R1 where I was doing that show interface command earlier. What we want to do is go to routers R1, R2, R3, and we want to configure each of those for full connectivity. So starting on R1, let's create a routing process. I'm going to say router EIGRP. And unlike OSPF, which would give a process number at this point, or process ID, this is an autonomous system number. This has to match on my neighbor. This number did not have to match if I said router OSPF1. My neighbor did not have to say router OSPF1. It could be router OSPF12. But here, this is an autonomous system number. It's got to match on my neighbor. So I'm going to make my autonomous system number 1. And if I want that top interface to participate, I'm going to say network 192.168.1.0. That's the network address space. And remember how wildcard masks work? For each octet, we subtract the wildcard mask value from 255. So if I've got I'll subtract the subnet mask value from 255. So if my subnet mask is 255.255.255.0, my wildcard mask is going to be 0.0.0.255. In other words, 255 minus 255 in the first octet, 0. 255 minus 255 in the second octet, 0. 255 minus 255 in the third octet, 0. 255 minus 0 in the fourth octet, 255. So that's going to be 0.0.0.255. Let's give a network statement for that bottom network. I'll say network 192.0.2.0. Here, it's a /30 network. In other words, that's going to be 255.255.255.255.252. If I subtract each octet in that subnet mask from a 255, that's going to give me a 0.0.0.3 255 minus 252 is 3. All right. By the way, when I give these network statements, like I mentioned earlier, I am not saying advertise these networks. Now, in this case, that's the effect. But I'm not saying advertise these networks. What I'm saying is, here is an IP address space. And if we have an active interface on this router whose IP address falls within this address space, advertise that network. And this is typically the way we do it, but I just want you to understand that the network command is not explicitly saying advertise this network. Let's move on to router R2 now. On a router R2, I've got to give a matching autonomous system number. I'll say router EIGRP 1. And just to prove what I was saying earlier about how the network statement did not say advertise this network, it was saying here's an address space, and if you have an interface whose IP address falls within this address space, I want to advertise that interface's network. Let me prove it. I'm going to say network, and I'm going to give an IP address wildcard combination that encompasses all possible IP version 4 addresses. I'm going to say network is 0.0.0.0, 255.255.255.255. That's everything. That's all possible IP version 4 addresses. Oh, and notice I just formed an adjacency with R1. That's good news. Let's go to R3. On R3, give a similar configuration. I'll say router EIGRP matching autonomous system number of 1. And again, I'll use that shortcut. I'll just say network 0.0.0.0 wildcard mask of all 255s. And we should see an adjacency pop up there. There it is. Nice. Now, let's take a look at some of those tables I was telling you about earlier. I could say show IP EIGRP. In fact, let me do this on router R2 because it's got a couple of neighbors. On router R2, let's do a show IP EIGRP neighbors. And you see that we've got a couple of neighbors. And you can see what the remaining hold time is for each of those neighbors. I was saying that we would start around 15, even though I never see 15 here, I always see 14. It counts down to about 10. A hello message is received, and we reset. So let me just give this command repeatedly. And we're probably going to see it count down from about 14 to 10 and then reset. So let's see. All right, 12, 13, 11, 11, 14, 10, 12, 14. Yeah, you see it goes down to about 10 and then it resets to 14. So that's a look at our timers in action. I could also say show IP EIGRP interfaces. That'll show me what interfaces are participating in EIGRP. And here it's gig 0/1 and 0/2. I could say show IP EIGRP topology to see what networks have been known or been learned by EIGRP. And for each of these entries, notice that we have 2 numbers here. This first number, that's the feasible distance. And this next number, that is the reported distance from my neighbor. So if I wanted to get to 192.168.1.0, for example, my feasible distance to get there is 3,072. But my neighbor that told me about the way there, it reported that its distance is 2,816. And if I look at the IP routing table, you'll notice that any networks that have been learned via EIGRP have a D after them. My guess is because of it stands for dual, uses the diffusing update algorithm. But there's a D there for every network that was learned via EIGRP. So that is a look at the configuration, a traditional configuration for EIGRP. Let me clear that topology off of the screen. In our next module, we want to talk about EIGRP stub routing, and that's quite different than OSPF stub areas. The idea is if we make an EIGRP speaking router a stub router, then it's not going to be queried. Now, where might it be appropriate to make a router a stub router? Take a look at this topology on screen. If we did not have a feasible successor to a particular route, we know that we could send out queries throughout the network to say, hey, do you know a way to get there? Do you know a backup path to get to this network? Well, if we have a router that does not connect to any other routers, we might not want to query that router. So what we can do is make that router a stub router. We can configure it for stub routing. So let me ask you, in this topology, we've got R1, R2, R3, R4. Would any of these routers, or multiple of these routers, or maybe just one router, would any of these be appropriate to configure for stub routing? Think about that. Is there any router that does not connect out to another router? I would suggest that R1 would be a good candidate, because R1 does not connect out to any other routers. R2 connects to R1, but R2 would not need to send a query to R1 because R1 doesn't connect to anybody else. It doesn't connect to any other routers. Now, some people, I've had students in some of these courses say, oh yeah, R3 and R4, they could be stub routers. Not really, because R3 connects to R4 and vice versa. They do have an adjacency beyond themselves. So those would not be good candidates for stub routing. And this is going to help confine the scope of how far those queries go out through the network. So let's see how we might set that up. We're going to go into router configuration mode for EIGRP, and we're going to say EIGRP Stub. And if we just press enter, suddenly that router, we're saying don't query me, and I'm saying I'm not going to advertise any routes. Now, in a lot of cases, we want to advertise any directly connected routes that stub router knows about. I mean, after all, if it's connected out to one other network going out to end users, I probably want to advertise that network. So I might give an option like connected. Or if I have a static route, I could say advertise a static. Or I could say if I want to advertise a summary route. We'll talk about summary routes in a moment. There's some other options there, but normally I'll say I want to do EIGRP Stub connected. That's what I do most of the time, where I'm saying, yeah, don't query me, but I'll still advertise networks that I am personally connected to. And I'd like to show you how to configure that. So let's go out to a live interface, and we'll just use our same topology, and I'll take my face off the screen so we can see a bit better. But the first thing I want to do here let's go back to router R1 for a second. That will be a good candidate to be a stub router, I think, because if you'll, actually, let me show you the topology. If you notice R1, it does not connect up to any other router. So R2 would not need to send a query to R1 because R1 doesn't connect to anybody else. R1, we may want it to advertise its connected network of 192.168.1.0/24. Here's how we could set that up. I'm going to go into the router config that we already set up on R1. I'll say router EIGRP Autonomous System 1, and I'll say EIGRP Stub. Notice the different options here. I want to advertise connected routes, which in this case is 192.168.1.0/24. Now, something else we might want to do on that same interface, since it does not connect, and notice it reset the adjacency when we did that, because it does not connect out to any other routers out of gig 0/1, would I really want to be sending hello messages out of that interface? Well, for performance reasons, that wouldn't be a good thing. And for security reasons, that could be a bad thing as well, because from a security perspective, what if somebody just added a rogue EIGRP speaking router to the network, and they formed an adjacency with R1 coming into gig 0/1? We don't want that. So what I can do is say, I want to make that interface a passive interface. I'm not saying I don't want to advertise it. I'm just saying I don't want it to send or receive hello messages. So I'll say passive interface gig 0/1. Now I could do the same thing on R3. That will be another good candidate as a stub router. I could set up gig 0/2 on R3 as a passive interface, but I'll just do it on R1 to show you how that looks. Now let's go to R2 and see how things look from the perspective of R2. On R2, I'll say show IP EIGRP neighbors, and I'll give the detail keyword. And you'll notice it said this neighbor of 192.0.2.1, that's R1, it is a stub peer, and it's advertising connected routes. So we can see that it is a stub router. So if R2 is looking in desperation for a way to get to a network that it's lost, it's not going to bother R1 because we've already declared R1 as a stub router. So that is a look at stub routing with EIGRP. And next up, let's talk about load balancing. We said that this made EIGRP very unique. I don't know another routing protocol that works like this or can be configured as easily as this to load balance across unequal cost paths. Now, please hear me. By default, EIGRP is going to pick the best path, the lowest metric. So by default, this doesn't happen. You need to configure this feature. It's called the variance feature. And the idea is you can say, I want to take my best metric, my lowest metric, my feasible successor's feasible distance, in other words, the lowest number I have for a feasible distance. And I'm going to multiply that by a factor. And that's going to create a range. For example, here, let's say I've got two different paths to get from R2 down to that SW3 switch that looks like it's on the 10.10.10.0/24 network. I could get there via R3. I could get there via R4. If I went there via R3, my feasible distance is about 10.5 million. If I went there via R4, my feasible distance is about 5.5 million. Okay. Obviously, I want to go through R4 because that's got a much lower feasible distance. However, if I wanted to use R3 some and not just let it sit there dormant, waiting for R4 to fail, what I could do is add the feature of variance. I say variance 2 in this example, and when I say variance 2, I'm saying take that feasible distance of my successor route, which is about 5.5 million, multiply it by 2. And if I multiply 5.5 million by 2, that gives me around 11 million. Now I've got a range. I've got specifically anything under 11,28,992, anything less than that, any backup route that has a feasible distance less than that, I'll use it too. It's not just the lowest feasible distance. It's any feasible distance that's less than that 11 million and change value that you see on screen. Now, you might argue, hold on, there's a reason that link to R3 has a higher feasible distance. Something's not as good with it. It doesn't have as much bandwidth. It has more load. Something's wrong with it as compared to the other link. Well, I would agree that it's not as optimal a link because it does have a higher feasible distance. But the variance feature knows about that. It knows how to account for that. So the variance feature is going to say, all right, I'm going to send a proportional amount of traffic to R4 and R3. So it's going to be sending nearly twice as much traffic via R4 as compared to R3. It's going to balance it based on the feasible distances. But the variance feature sets a range, and if any backup path falls within that range, we're going to use that backup path. Pretty cool feature of EIGRP. And to set it up, you see we're in router configuration mode, and we simply say variance 2. Variance 2. Next up, let's talk about summarization. And we talked about this in our OSPF deep dive session as well. We said that instead of advertising a lot of individual routes, especially in something like a service provider environment, we may want to summarize those networks. And when I say summarize those networks, I mean, let's take a look at these. Let me give you an example here on screen. Let's take a look at 172.16.3.0.2.0.1.0.0.0/24. They all have a lot of bits in common. We can see exactly how many here in a few moments. 10.1.1.0, 10.1.1.4, 10.1.1.8, 10.1.1.12. They got a lot of bits in common. Instead of advertising each of those individual networks, what if I sent a summary advertisement? That's going to cut down on the overhead. In fact, let's take a look at some of the advantages that we get from route summarization. Number one, it's going to help keep our routing table smaller. Instead of having a lot of individual routes, we can have one summary route. And if we're going to an IP address whose IP address lives within that summary address range, then we're going to go to wherever that summary route says to go. We don't need those individual routes. Now, when we're when we're doing summarization, it's best that we think of that up front as we're initially laying out the IP addressing scheme for the network. Because if I've got like a 10 dot network over here and another 10 dot network over here using different subnets, that can cause a problem. If I tried to do summarization and I tried to summarize too broadly, it's going to be pointing in two different directions, and that's not going to work. So let's think about this in advance. I'll give an example here, and we'll show you how to set it up. But here's the cool thing. Remember OSPF? We can do route summarization only on an autonomous system boundary router and on an area border router, either one of those. Here, it can be done on any router. And in addition to reducing the size of the routing table, it's going to reduce the scope of those queries that are sent out. They're not going to be sent out as far. That's going to help with our processing on our routers. And keep in mind, it could cause suboptimal routing if you're saying, if R1 is advertising a summary route to R2, but there is a network that falls within that summary address that lives off of R3 in the other direction, that's going to be a problem. So we don't want to summarize and have that summary address include something that doesn't live in that direction. So let's be careful with that. And EIGRP does have the ability to do auto summarization. Sometimes we want to turn that off. But in this example, I want to take this topology that we're seeing here, and let's do some network summarization. For example, let's say we want to summarize the networks of 172.16.0.0, .1.0, .2.0, .3.0. Obviously, all 8 bits in the first octet are the same. They all come out to 172. The next 8 bits in the second octet, they all come out to 16. So far, we've got 16 bits in common. Let's take a look at that third octet. In the third octet, we have values of 0, 1, 2, and 3. And I've put those for you in binary on screen. Notice that the first 6 bits in that third octet, they're all the same. They're all zeros. So 16 plus 6, we've got the first 22 bits in common. So a network address, you recall, is we've got zeros for all the host bits. So let's take those 22 bits that we have in common, and that leaves 10 host bits. We set all those to zeros, and that means that I could advertise a network of 172.0 or 172.16.0.0/22, and it's going to encompass all 4 of those networks. Let's see how to set that up. Let's go out to the live topology once again, and I'll bring up a different topology this time for summarization. I've got a different set of routers here. Let me go over to router R6 in this topology, and we'll see what it sees in its routing. I've already got EIGRP set up, by the way. If I do a show IP route, you'll notice that I've learned about 10.1.1.0, 10.1.1.4.8.12. I've learned about 172.16.0.0.1.0.2.0.3.0. It looks like we've got a couple of opportunities here to do some route summarization. And we've already seen in the previous slide that we could summarize all those 172.16 networks. They could be summarized as 172.16.0.0/22. /22 subnet mask, that's 255.255.252.0. Since those networks are coming into router R5, that might be a good place to do the summarization. And what we're going to do is go into the interface. It's going to be sending out that summary advertisement, which is gig, it's not on screen, but it's gig 0/5 on R5. So let's go to router R5 in this topology. And let's go into global configuration mode. And I'll go into interface gig 0/5. And from there, I'm going to say IP summary -address. And I'm going to, I have to say what I'm summarizing. For EIGRP Autonomous System 1, I'm going to be sending the summary advertisement of 172.16.0.0. with a /22 mask, which is 255.255.255.252. Well, actually, I had one too many 255s in there. It's 255.255.252.0. There we go. It'll reestablish the adjacency. Let's give it a moment to do that. So it said it did a resync there. And let's go back and see what the routing table on R6 looks like now. over on R6, if I do a show IP route, look at this. Instead of seeing all those individual 172.16 networks, now I've got this summarized network, 172.16.0.0/22. So if I want to get to any of those individual IP addresses that live in that address space, this is going to get me there. It's going to get me there. However, you'll notice that we still have all of these 10.1.1 routes. They're still advertised individually. Let's do a manual summarization on those. So I talked about how to do actually, let's do it this way. Let's do an automatic summarization on those. I said EIGRP could do automatic summarizations. Here's how we can do that. Over on R5, let's go back over to R5. What I'm going to do here is do a show IP protocols. I want to show you a before and after here. If I do a show IP protocols, notice that EIGRP, Autonomous System 1, has automatic summarization currently disabled. If I enable it, it's going to automatically summarize those 10.1.1 networks. Check it out. I'm going to say configure terminal, router EIGRP Autonomous System 1. I'm going to say auto-summary. That's it. That's going to do my automatic summarization. We're resetting our neighborships there. And after all that resynchronization has happened, let's go back to R6 and check out our routing table once again. Let's do another show IP route. Yeah, and here, look at this. We've automatically summarized at the classful boundary, 10.0.0.0/8. Now, this is where we could get in trouble if we had discontiguous subnets of this classful network. If I had a 10.100.100.0/24 network hanging off of R6, this would be a problem. But it's not in this case, because all those networks are living in the same direction. So that's a look at how to do manual summarization and automatic summarization. Now let's pop back over to our slides and let's talk about EIGRP for IP version 6 configuration. EIGRP for IP version 6. We said that EIGRP had the ability to route for more than one routed protocol. For example, it can route for both IP version 4 and IP version 6. And the traditional way of setting that up is to configure those individually. We set up routing for IP version 4, and then we turn around and set it up for IP version 6. That is the traditional way of doing it. With IP version 6, we're going to be using the link local addresses on those links. Our neighbor is going to be known by their link local address. There's not going to be the auto summarization that we talked about that IP version 4 has. And unlike IP version 4, the neighbors don't necessarily have to be on the same link, the same network segment. And we've already mentioned earlier in the course that we're going to be sending updates to the multicast address of FF02::A. So let's go back out live once again, and we'll use our same topology that we did IP version 4 configuration on earlier. Let me find the right topology for us here. One second. There we go. It's the same topology, except now I'm showing the IP version 6 addresses that we have. We've already got EIGRP for IP version 4 configured. Now we're just going to overlay that with EIGRP for IP version 6. And one of the first things we have to do that's might be surprising if you haven't worked much with IP version 6 is we have to first enable IP version 6 routing. It's not enabled by default on our routers. And to do that in global configuration mode, we're going to say IPv6 unicast-routing. Now I'm going to create that EIGRP for IP version 6 routing process. Instead of saying router EIGRP and giving an autonomous system number, I say IPv6 router EIGRP and give an autonomous system number. Now, I just happen to use the same autonomous system number as I did for IP version 4. It doesn't have to be. They're not related. I just start at one so I can remember it easily. And there's a lot of stuff that we can set up here. We could set up things like our maximum paths over which we can load balance. We'll set up variants here. We'll set up our passive interface here. But there's one thing that's conspicuously absent. There's no network statement. How do we make an interface participate in this EIGRP process if there's no network statement? Well, as I mentioned earlier, the network statement was not really saying advertise this network. It was setting an IP address space, and we said if an interface had an IP address which belonged to that IP address space, then we want to advertise that interface's network. So what we were really doing with the network statement was making an interface participate in the process. So how we do it here is we go directly to the interface. We go into interface configuration mode. I'll go into interface gigabit 0/1, and I'm going to say, I want you to participate in EIGRP Autonomous System 1. I'll say IPv6 EIGRP 1. Or again, 1, that is the autonomous system number. Let's go do the same thing for interface gigabit 0/2 on R1. IPv6 EIGRP Autonomous System 1. Let's go give a very similar configuration now on routers R2 and R3. On R2, again, I'll say IPv6 unicast routing, IPv6 EIGRP, or router EIGRP, a matching autonomous system number. And let's go back into the interface gig 0/1, and it's going to be IPv6 EIGRP Autonomous System 1. Let's go into gigabit 0/, oh, we got an adjacency. That's good news. 0/2, same thing. 1 router to go. We'll say IPv6 unicast -routing, IPv6 router EIGRP Autonomous System 1, interface gigabit 0/1, IPv6 EIGRP Autonomous System 1, same thing for gigabit 0/2, and I think we are good. Now, let's give some verification commands, shall we? Let's do a show IPv6 route. Instead of saying show IP route, it's show IPv6 route. And again, networks that have been learned via EIGRP, they're indicated with the D flag. And here we're on R3, we've learned about 2000:1:/64. That's the network off the top of R1, going from R1 up to SW1. We've also learned about 2000:2:/64. That's the network between R1 and R2. We can look at our protocols. I'll say a show IPv6 protocols command. And you'll see that we're routing for EIGRP Autonomous System 1. If I say show IPv6 EIGRP neighbors, you'll see that I've got one neighbor and it shows up with its link local address. And we can take a look at the interfaces in detail. Let's take a look at the interfaces and then we'll look at them in detail. I'll say show IPv6 EIGRP interfaces. And I've got my 2 interfaces participating. I could give the detail keyword, and that's going to give me some additional information. I can look at the topology, show IPv6 EIGRP topology. Basically the same verification commands we had with EIGRP for IP version 4, except instead of saying IP, we say IPv6. Now, this is the traditional way of setting things up. What I want to do now is show you how to set up named EIGRP where we use address families. Now, one of the great things about named EIGRP is that it is compatible with traditional EIGRP configuration methods. Now, for named EIGRP configuration, we're going to be able to go into different configuration modes. We can go into interface configuration mode and set up things maybe like timers, and those would be inherited down into our different address families. We can have an address family for IP version 4, for IP version 6. Together, this is all called an EIGRP virtual instance. And the cool thing about it is, this virtual instance contains all of our EIGRP configuration settings. We don't have to go into interface configuration mode. We do everything from one spot. Now, as just a few examples, this is not comprehensive, but if we go into address family configuration mode, we might set up the router ID maybe a stub router. We might go into address family interface configuration mode, set up things like our timers. We could go into address family topology configuration mode to set up things like variants to set up redistribution. I want to take you back out live again, and let's set this up. First, I want to get rid of our existing configuration. And you know what? I'm just going to get rid of it on R2 because, as I was mentioning earlier, named EIGRP is compatible with the prior versions of EIGRP that we've already set up. So I'm going to leave our existing configs on R1 and R3. I'm just going to change up R2. Let's go into R2, and I'll say no router EIGRP1, no IPv6 router EIGRP1. And now let's configure named EIGRP. Step one is we create a virtual instance. So in global configuration mode, I'm going to say router EIGRP, and I'm going to give a name of this instance. I'll just call it R2 demo. And give some context-sensitive help. And as you can see from this context-sensitive help, not much happens within router configuration mode. Most of the work is done within address family configuration mode, and we want to create an address family for both IP version 4 and for IP version 6. So let's say first address-family, and you see those are our two options, IPv4 and IPv6. For IP version 4, I'm going to say unicast. I'm setting up unicast routing for IP version 4. And it's going to be for autonomous system 1. Now we're in address family configuration mode. And you can see there's a variety of things that we could set up within address family configuration mode. For example, I could set up, or I could go into address family interface configuration mode and set some things up there for different interfaces. Or I could go into the default configuration mode. Check this out. I'll say address family interface default. Now, parameters that I give here, like timers, those are going to be inherited down to all the interfaces within this address family. And if I go into the actual interface instead of AF interface default, if I go into a specific interface, yeah, I could override the defaults. But again, here's where I would set up things like my timers. Like here's the hold time. Here's the hello interval. I could set up a passive interface here. And even though I really don't want to make any changes here, those are the types of things we could set up. Now, another configuration mode that we could enter is address family topology configuration mode. From there, we set up things that impact our EIGRP topology. For example, let's see how to configure our base topology. It's typically what we do. I'll say, let me exit out of this, and I'll say topology base. I could set up variants here. I'll say variants 2 as an example. Now, something we haven't done yet is to say what interfaces we want to participate in EIGRP. We can do that from within address family configuration mode. I'll just give a network statement that encompasses all the interfaces, and as soon as I do, bam, we should see a couple of adjacencies come up. So let's go in, let's see, I'm in, let me go back into my configuration mode here. I think I was in the IP version 4 address family. So let me re-enter that mode. Okay, for the IP version 4 address family, I do have the network statement now. I'll say network 0.0.0.0, 255.255.255.255. Remember, that encompasses all possible IP version 4 addresses. And it seems we have a couple of adjacencies. Excellent. Now, that's all I really want to do for IP version 4. Let's focus on the IP version 6 address family now. I'll say address-family IPv6 unicast autonomous system 1. And check this out. Without doing anything else, I've got adjacencies that just came up. How did that happen? Well, that is surprising. But what's going on is with IP version, or with named EIGRP for IP version 6, it makes all interfaces automatically participate in that IPv6 EIGRP process as soon as we create the address family for it. So really, that's all I have to do to get it set up for IP version 6. Kind of wild. Now, after specifying the autonomous systems, or after specifying what I want to do for my address families, there's not a lot that we need to do. Everything's come up. We could set up something with the base topology, though. I'll say topology base to, let's see, just topology base, I should say. And I'll say variance 2. So for IP version 6, I'm setting up a variance value of a 2. And when we're done, I could say show run pipe to section router EIGRP. And check this out. This is a beautiful thing about named EIGRP. All of our router configuration is contained within one hierarchical structure. We've got this virtual instance called R2 demo, and it's got all of our configuration for IP version 4 and all of our configuration for IP version 6 routing as well. I could do a show IP protocols command, and you're going to see some similar information, but something I wanted to point out here is we now have another K value. We've got a K6 value. This is going to allow us to support something called wide metrics. And this is probably what we want to start doing with our newer configurations, because as we exceed speeds of around, I think it's around 10 gigabits per second, EIGRP in its older form is not able to distinguish between like a 10 gig link and a 40 gig link and a 100 gig link. We need to use wide metrics to do that. And that's supported with named EIGRP. Let's give some verification commands. Let's say show IP EIGRP interfaces. And it shows us those are the interfaces for IP version 4. If I want to see IP version 6, I'll say show IPv6 EIGRP interfaces. So the same verification commands work even though I've used named EIGRP. I could say show IPv6 EIGRP neighbors. Notice the link local addresses, or I could just say show IP EIGRP neighbors, and there's our IP version 4 addresses. All right, just a few examples of some show commands. And if I do a show IP route, again, we should have learned some routes via EIGRP, and those are indicated with this D flag. All right, one other topic that we want to touch on before we start to wrap it up today, and that is authentication for EIGRP. We don't want somebody to just come along and add a rogue router to the network and start advertising EIGRP routes that are false, that might direct an unsuspecting user to the attacker's router or to the attacker's computer. Now, there's two types of authentication we've got. We've got plain text and hash-based. Let me give you an idea of why we might need this. Let me visually show you what I was talking about. With plain text authentication, we've got a key, a pre-shared key on both of our routers. And with plain text authentication, when we send a routing update, we send in plain text is the bad news. We send the key to say, all right, here's like the password. And if our keys match, then yeah, you can accept my routing update. The bad news is, what if the keys match, but they're coming from an attacker? An attacker could come along and they could do what is called a man-in-the-middle attack, or sometimes called an on-path attack. But what they could do is convince R1 to send it traffic going over to R2. Different ways of doing this. The first one that comes to mind is we could overflow the MAC address table on switch SW1. So anybody that connects brand new to that, their MAC address is not going to be learnable because the MAC address table is full. There's different ways of doing it. We could do gratuitous ARPs, but through some method, one of many methods, that man in the middle is able to intercept traffic going between R1 and R2. And because the key is in plain text, they just learned that key. They could introduce then their own rogue router, configure it with the key that they just learned because it was in plain text after all. And suddenly that rogue router would be authenticated by R2, and we could start sending false updates to R2 and to R1. This plain text authentication, it's supported in RIP version 2, OSPF version 2, and intermediate system to intermediate system. We probably don't want to use it though. We want to use hash-based authentication. With hash-based authentication, we're not sending the shared key across the network. What we're doing instead is we're sending a hash value of the key or a hash digest of the key. We're running it through an algorithm like MD5, Message Digest 5, or SHA, Secure Hash Algorithm. So what we do is we take the routing update and the local key, and we run it through this hashing algorithm. MD5, for example, it's going to produce a 128-bit hash digest. And if both sides create the same hash digest, it's a good indication that both sides have the same local key. So we're not sending the key in clear text across the network. We're sending the hashed value of a combination of the routing update and the key. And if the hash digests match, we realize that the routing update is probably valid. Now, this kind of thing is going to be supported in several different routing protocols out there. We're going to be able to support MD5 in the different, I won't read through the bullets, but you see all the different protocols that support MD5. Now, SHA is also supported, but not as widely supported on Cisco gear as what I've indicated on screen. You see, in Cisco iOS, RIP-NG and OSPF version 3, they don't natively use secure hash algorithm. They don't natively use SHA. Instead, they rely on IPsec that can use SHA because IPsec is part of the way IPv6 protects routing protocols. But I wanted to list it here because there are some RFCs out there that suggest that, yes, you can run SHA with these routing protocols, even though it might not be something you set up on your Cisco router. But let's say that we do have one of these shared keys, whether we're sending it in clear text, hopefully not, or whether we're hashing it. What if one of those keys becomes compromised? Do we have to go around and then update everything? Well, what we can do instead is just set a lifetime for how long a key is going to be valid. We could set what is called a key chain. A key chain is going to allow us to specify the duration over which a key is going to be valid. And then it's going to expire and another key is going to take over. You could have multiple keys valid at different times on the same key chain. And I want to show you how to set that up. Now let's go ahead and take a look at an authentication example. I'll bring the topology back up on screen. And let's set up a key chain on R1. I'll say we've got a key chain with the name of R1 key chain. I know, real imaginative. And I'll say for key number 1, I want to have a key string of primary underscore key. And I want to say what is the accept lifetime when I will accept this key from a neighbor, and what is the send lifetime? How long am I going to be sending this key to a neighbor? So we'll say, first of all, accept lifetime. And I'll say it's going to start at midnight, 00:00:00 on January 1st, 2022. And it's going to end on midnight, 00:00:00 on February the 1st, 2022. That was the accept lifetime. Let's do the send lifetime. We'll make it the same. Now we'll say for key number 2, I want to create a key string of secondary key. And this accept lifetime, let's make it overlap a little bit so we don't have any period where no key is valid. Instead of waiting until midnight on February the 1st, let's do midnight on January the 31st. So there's a day in which both keys are going to be valid. I'll say accept lifetime is going to be midnight 000000 January 31st, 2022. And I want to make this be for infinity. We'll not have another key set for this. This will just take over until we change it. I'll say duration is infinity. That was accept lifetime. Let's set the send lifetime to the same. And we can verify our config with a show key chain command. We see key 1 is primary underscore key. The backup is secondary key. And we see the valid lifetimes. And it says that key number 1 is currently valid, which is what we wanted. Now let's go over to R2 and give a similar configuration. On R2, remember, we're configured using named EIGRP, so it's going to be just a little bit different, but it's still going to be compatible. We'll go into global configuration mode, and I'll say router EIGRP, and we'll give our virtual instance name of R2 demo. And I'm going to go into address family for IP version 4 configuration. I'll say address-family IP version 4. Unicast autonomous system was 1, and I want to go in specifically to interface gig 0/1. That's what's going to be doing authentication up to router R1. So I'll say address family interface gig 0/1, and I want to set it up for MD5 authentication. So we'll say authentication mode, and notice that with named EIGRP, I could do SHA or MD5. To make it match, I need to do MD5 here. I'll say mode is MD5. And now I want to do authentication using a keychain of R2. Keychain is what I think I called it. And that should bring up the, oh, and it did. It brought up the new adjacency, confirming that our authentication is working. And that's a look at configuring EIGRP with a traditional approach for IP version 4 and IP version 6, and also how to use the name configuration approach.